Hello, this video is entitled Optimization Problems. It's taking sort of application problems and using calculus, namely the derivative, to find minimums and maximums of situations that would be guaranteed by the use of the derivative. Now, for the most part, the applied min and max problems will sort of come in this particular form. There could be exceptions to that. But you'll have information where you can come up with what this book calls the primary equation, the function you're trying to maximize or minimize. So like here's just something I made up. A equals 2 times xy. A would probably be area in this kind of problem, and S equals x squared plus 5xy. That could be for two numerical values that satisfy a certain situation. Well, the problem with these equations is we can't do much with it because we have multivariables, and multivariable functions aren't addressed until calculus 3. But then we need some sort of, a secondary equation or some other information, whether it's, when I say equation, it means it's given information to you be able to create an equation. You might not be looking at an equation. For example, it might say two numbers that have a sum of 10. Well, then you would turn that into x plus y equals 10. So we need that information because then you can go back and substitute y in terms of x, or you could do x in terms of y, into this equation, and then you get it down to one variable, and that's when we can take the derivative. So the key will be reading the problem, getting this information, substituting, and then have it down to one variable, then take the derivative. All right, so Stewie says the minimum or maximum values will be obtained from critical values and relative extrema. So it's all about the critical values. So let's take a look at this one. Find two numbers given the sum of the first number squared and twice the second number is 36, and the product of the two numbers is a maximum. That's telling you here both numbers are positive, so sometimes we have to watch for that those kind of instructions. So obviously any particular negative critical value we get, we would eliminate. Now the choice, the fact I use variable p, that's the least of your concerns here. The p equals xy. The x times y is important, but the p can be any sort of arbitrary value variable. And then here's the subject 2. That's indicating the information from the secondary equation, also known as the constraint equation. All right, so this is where you have the first, so I'm letting the first number be x, the second number be y. You could actually reverse that if you wanted to, it wouldn't hurt. But the first number squared would be x squared, and twice the second number would be 2 times y, and is 36. So is means equal, so we have this information though, x squared plus 2y equals 36. So now what I'm going to do is I'm going to take the secondary equation, the constraint equation. I'm going to solve that for y in terms of x. So that's pretty simple algebra. Y equals 1/2 times 36 minus x squared. So we substitute this equation right here in for y over here into the objective function that we're trying to maximize or minimize, in this case maximum. Now this is not necessary that you change it to p of x, but it would be a true statement because once you substitute this in for y, your only variable is x. But that's not mandatory. I just often like to do that. So you just take this, multiply it out, basic algebra, you'll get 18x minus 1/2 x cubed. Okay, so everything's happening from the critical numbers. So let's take the derivative and see what we got here. So the derivative of this would be p prime of x equals 18 minus 3/2 x squared. So to find our critical number, we'll set that equal to 0. And then you'll end up with x squared equals 12. And you know, in other videos, I've kind of made a big deal about don't forget the plus and minus when you solve this kind of equation. Well, in this case, that's not necessary because the problem is defining these both as positive. So your other things we did, like increasing, decreasing, concavity, every number counts. But sometimes in these sort of problems, you don't necessarily need every number. Now here they're telling us both are positive. Sometimes in other problems, you kind of use common sense. If it's something where we're trying to deal with measurements, say for length, for example, some sort of dimension like that, well, then the value has to be positive. They don't have to tell you it's positive. Has to be positive. So that's why I don't have the plus and minus here. It's only going to be this number. So no one said these had to be integers or anything like that. It just said two positive numbers. So square root of 12 is fine. That's okay on a handwritten test. I'd have no problem with that. 2 root 3 is just a simplified version of that. So that's your x. Then to get your y, you have this equation for y right here and just substitute that value right in for x, and you'll get 12. So basically what this problem is saying, with 2 root 3 and 12, that the product of those numbers is a maximum given. So the square of the first one, the square root of 12 squared would be 12, plus 2 times 12 will be 36. So in other words, when you multiply those together, that would be 24 root 3. So what that's saying is calculus has shown us you could sit here all day long and you could make up different x's and y's that satisfied this equation right here without much trouble. You could sit there and make up different x's and y's, but I guarantee you would not get a larger product result than this. Like if I made one up and said, oh, what if I let x be 4 and let y be 10? That would work. 4 squared plus 2 times 10 would equal 36. And then you multiply 4 times 10, so that gives you a value of 40. Well, check this in a calculator, but I promise you that 12 times 2 square root of 3, in other words, 24 square root of 3, is a number larger than 40. You're not going to beat 12 square root of 3. I might as well go ahead and do it here just to show you. Obviously, you could have checked this yourself, but no trouble to do this real quick. This will be a number larger than 40. There it is. So no combination of x and y's are going to beat that number as far as the maximum. No chance. All thanks to calculus. Now, if you wanted to verify, you don't really have to. But this is just showing you how you could do this. In other words, from something we learned in the previous section with the second derivative, you can use the second derivative test, or you could do critical number, sign chart. You can do it that way too. But the second derivative test, you can go back and look over that in the section with concavity and inflection. It's in those notes or in that video. So if I took the next derivative of this function right here, 2 comes down, kills the 2, it'd be negative 3x. So p double prime is negative 3x, and this was the rule for second derivative test, and I explain why it works this way in that video. But if you put the critical number in, you get a negative, that's actually a maximum. Put a positive in there, it's actually a minimum. And if you put the x in there, which is square root of 12, negative 3 square root of 12, who cares what it is? It's obviously a negative number, and therefore that makes it a maximum. So that's guaranteeing that it's a maximum. All right. So let's see what we have here with this example. All right, let's see what we have here. In this one, we have I just kind of joked about chickens and rabbits or whatever, but that's not really part of the problem. But what we're trying to do here is we're trying to fence this area off and we have 400 yards of fencing, and so we have the 2 long sides, which I wrote as 2 short sides, these 3 sides. So we have that much fence to put out, but we want to know what dimensions then would maximize the total area. Now, I'm mentioning you don't have to worry about any such factors as the thickness of the fence or anything like that. So let's see what we have here. Let's see. So you see, I could have used, I guess, 1 long side there as X. You can do that also, I guess. But I split it up as 2 equal sections. So there's 4 X's and there's 3 Y's. And therefore, the area that we're trying to maximize is 2X times Y. So I guess we used 1 side for X, and it would just be X times Y. And then now, the secondary or constraint equation would be either 4X's plus 3Y's has to add up to equal to 400. So we take the Y, solve for the Y in terms of X, and then we're going to plug it back into this equation. So do a little algebra here. That's easy enough. Y equals 1/3 times 400 minus 4X, which we're now going to plug in for that Y, and that means our area equation will look like this. And once again, I just called it A of X. You didn't have to, but I generally do. So now we just do a little algebra there and distribute this. So basically, it's 2X over 3 times everything on the parentheses. You get 800 over 3X minus 8/3 X squared. And it's all about the derivative. So let's take the derivative. A prime of X equals 800 over 3 minus 16 over 3 times X. Set this equal to 0. Let's see, I moved the 16 over 3X to the other side. Made it positive. And just multiply both sides by 3 over 16. And that works out to be a nice, clean answer of 50. And then to get the Y, we take that X, and we already, we're always solving for Y in terms of X. I mean, you could go back to the original equation, but you don't have to since you have this. So we have Y and plug that in for Y. So plug in the 50, and you get 200 over 3, which is fine. That's the way I usually do it. I'm not a big fan of mixed fractions, but I guess it doesn't hurt. So 200 over 3 is the same thing as 66 2/3. So those would be the dimensions of the X for the X's and the Y. So I guess if you were addressing this, that means the entire length of that side where I called it 2 X's, then it would actually be 100. So if we did it that way, you would say then each, if you said 100 on each of the 2 long sides, like so, 100 all the way across, and then 66 2/3, 200 over 3, or each of those Y sides. Now we're asking ourselves, if you do this right, you're not going to have to verify that it's a maximum. If you do everything correctly, it's not something you have to do. But this one's really easy, because we take the second derivative, so here's A prime of X. Second derivative is negative 16 over 3, so yeah, it's negative. So therefore, negative means it is a maximum. And this is showing you what if we wanted to know what the total area then is. So that could also be asked, is what would that area be? So the area function was 2 times X times Y. So, okay, it's a weird, so 20,000 over 3, or it'd be this number right here, 666 2/3 square yards. This thing in the calculator is not that important, but because one thing about this thing in the calculator, though, that doesn't assume X doesn't have to be a whole number either, but obviously just to show it, I made them whole numbers. You see, like the Y is not a whole number, so X doesn't have to be a whole number either, but just kind of gives you an idea that you can see at 50, it's producing the largest area. But even though you might could argue, well, how do you know it's not 50? Okay, that would be a good argument. But mathematically, it's clearly 50. So, but that's showing the. You see, it's smaller before, and it starts decreasing after 50. All right, now we're going to take a fencing problem where we're just fencing three sides. Maybe we're bounded by either a wall or some sort of river or something like that where we don't have to fence the fourth side. And I'm saying we've got cattle in there this time. Maybe if you have it along the river where they can drink, you don't have to fence the riverside. Now, these kind of problems, I don't like to do them where it's all four sides, because mathematically the answer is always a square. So I can derive that. It's simple enough to derive and prove. You could even try it yourself if you want to. I'm not going to for the purposes of this video. But it's always a square. So that's if you were ever trying to build something like the last problem where we had 400 yards of material and you want to maximize your area and only have one enclosure, make it a square. That'll guarantee you get the maximum area. So this one, we did this on purpose. We're only having this three sides. Now this is a little bit different. This one's actually giving you the area, and it wants us to find the, we want to minimize the total amount of fencing. So last problem we had the perimeter, the total fencing, and we wanted to maximize the area. So what we're trying to say here is we want 180,000 square meters in the least amount of total fencing we can have. Obviously, the least amount of fencing will give you the least cost. So let's see. So here's the, and once again, I'm just using P, whatever letter you want there, but we'd have, and once the question usually is asked is, those two X's could be Y's and the Y could be X. So it'd be okay. That would be all right. You would still get the right numbers representing the right length. That would be okay. So you could have an X here and then two Y's. And so, but the way I wrote it then would be 2x plus y, and subject to the constraint that x times y, the area of this whole thing, x times y, would be 180,000 square meters. So I solve for y in terms of x, which is 180,000 divided by x, but just for the purposes of the derivative, I'm leaving it as a negative exponent. It makes it a little easier. So that's the same. So 180,000 x to the negative 1 would be the same thing. So you see I put that over in here for y. I take the derivative. So it'd be 2, and it'd be negative 180,000 x to the negative 2. I'm going to find the critical numbers by setting that equal to 0. And when we set this equal to 0 to solve for x, now I'm going to go ahead and change the exponent back to positive for the algebra purposes. For the derivative purposes, I liked it to be negative. I thought that was easier, obviously, than doing the quotient rule. But now I want it to be positive, and so just kind of move this over, set it equal to 2. Pretty basic algebra. You get 2x squared equals 180,000. X squared equals 90,000. And like I was saying earlier, they don't have to tell you in this problem that we only want positive values for the sides. Common sense would tell you. I don't think we can have negative 300 meters as a measurement. So we only want the positive square root of 90,000, which is 300. And then that would be, so then the y would be 180,000 divided by 300, which is 600. So the numbers worked out pretty well. I just did the second derivative test for this one, and it was positive, and that guarantees it's a minimum. But that was, like I said, didn't have to be done. So we would want to get the least amount of fencing and still get 180,000 square meters of area. We want 600 on the long side and 300 on the two short sides. So therefore, if the problem then also asks what is a total fencing, which I guess this is asking that, excuse me. And I guess I did not put that in there, did I? Well, it would be 1,200 total fencing. I think I should go back and edit that in there because you'd have 600 plus two sides of 300. So 12, I'll just write it here for now. 1,200 meters of linear fencing there that we would need total. Okay. All right. So let's look at a different type of problem. We want to take this function f of x equals the square root of x minus 8, and then we have a given point, 12 comma 0. We want to find the point on the graph of the square root of x minus 8 that would be the closest to that point 12, 0, the minimum distance. Now, I just kind of drew a rough sketch of where I thought it would be here. Obviously, we're not doing this as a guessing game. We're doing this using calculus. So there's the square root of x minus 8 graph. Here's where I put, so you see these are, I have the scale there, but those are about 4s. 4, 8, 12. There's 12, 0. So I just kind of drew a line generally pointing to roughly about where I would think it was going to be. I might be off a little bit, but that doesn't matter. If my picture's off, it just matters, the math matters. But it would be somewhere in this neighborhood. Obviously not, as you go out there, it's farther away. Here it's kind of close. It's tough to tell. Anyway, we're going to solve it. So we're going to minimize the distance. Now you see, I rewrote this, the coordinate, every coordinate on this graph, because y is already the square root of x minus 8. Every point can be written as x comma square root of x minus 8. So you see we already have everything in terms of variable x by doing this. Now we want to minimize the distance using the distance formula from the point to the graph. Now to make this easier, all we have to do is minimize the quantity under the radical. You see, here's our good old distance formula from back in algebra days. Because if you minimize the quantity under the radical, you're also minimizing the square root of that number at the same time. So we don't have to worry about the square root when we're taking the derivative and all that kind of business. That makes it a little bit easier. So here's the actual distance. It doesn't have to be in this order. You could reverse these two around. It's going to work out just fine because when you square this, everything becomes positive. So that the order of these two doesn't matter. So it's 12 comma 0 to x comma the square root of x minus 8. And here we go. So you have, so you see, I just call that d of x, and I just ditched the square root. So that means then, if you wanted to actually find the distance at the end, here we're just finding the point on the graph, but obviously to find the actual distance it is, you would need that square root back in there. And so here we have x minus 12 squared, the square root of x minus 8 minus 0 squared. So you kind of FOIL that out. You have x squared minus 24x plus 144 plus x minus 8. And then combine your like terms. You have x squared minus 23x plus 136. And then everything's about the derivative, so we take the derivative. So the derivative is 2x minus 23. So I'm going to set that equal to 0. And here I'm showing the second derivative being positive, therefore that guarantees it's a minimum. And so it's 23 over 2 would be the x coordinate. Then the y coordinate would be the square root of x minus 8. So the actual point on the graph would be 23 over 2 comma the square root of 7 over 2. Now, which, you could put to get the actual distance, you'd put the x in here, but then you'd have to square root it to get the actual distance. But all right, so my drawing's probably a little bit off here. Maybe thinking, 11.5 for x would be somewhere up about here, but it was kind of close. But anyway, that didn't matter. So that's all you have to do. Here's another one. We're taking the right half of your standard y equals x squared parabola, and we're trying to find the closest point to 0, 3. All right, we can do that. So that graph then, y equals x squared, can be written as a coordinate x comma x squared. So it'd be 0, 3 to x comma x squared. And once again, we're just going to minimize the quantity under the radical for the distance formula. So that's why I don't have the square root there. So it'd be x minus 0 squared, x squared minus 3 squared. So we x minus, okay, that's just x squared there for the first one, obviously. This one, you just kind of FOIL it out. You get x to the fourth minus 6x squared plus 9. There are a couple of x squared terms that are like terms. You can put those together. And notice we're saying that x is greater than or equal to 0. So you have your d of x is x to the fourth minus 5x squared plus 9, so the derivative would be 4x cubed minus 10x. So you set that equal to 0, you factor out a 2x, you'll have 2x squared minus 5 equals 0. And x equals 0, x squared equals 5 halves. When you set that equal to 0, which is plus and minus the square root of 5 halves, we definitely don't want the negative one because we're saying, it's in the first quadrant. So that's because it would have an equivalent answer in quadrant 2. If you had the entire parabola there, that'd be an answer in quadrant 2 that would match the one in quadrant 1 as far as the same distance, same minimum distance. I guess because I included 0, I guess what I could have done in this problem is just made x be strictly greater than 0 and eliminate this 0 answer. But I'm only keeping the 0 there because I have greater than or equal to 0 here. And so, but you can really easily take the, even with the 0 there, is do the second derivative test to figure out. It's very rare when you get 2 like this, but when you do, that's what you do, is you just take, you could do one of two things, actually. You could plug it into this equation right here for d of x and see which is the actual minimum, which is the lower of the two. And you can check it that way, because obviously the smaller of the two distances would be the minimum. I did it using the second derivative test. Easy second derivative, 12x squared minus 10. You put in 0, you get negative 10. You put in square root of 5 over 2, you get positive 20, so then that'd be max. So really, it's technically not the maximum distance, but whatever the case may be, we're looking for the, because obviously this goes on and on and on, as that graph goes on, the distance would increase. But anyway, but that worked out well, though. It clearly tells us which one's our minimum. In fact, I could probably just erase that, just eliminate any confusion here. And then therefore, so that the x will be the square root of 5 over 2, and since y equals x squared, y would just be 5 halves. Oh, there I'm actually testing the distance, or coming up with the actual distance. So see what I did, though, is I had to include the radical back in there if I wanted the numerical value of the distance. And so there we go. So that's kind of, I made a rough guess. Once again, that doesn't mean any. So square root of 5 over 2 is the value. Okay. And there we go. Now this is a classic problem here. This is very common in these sort of problems. It's a good one to, I've put this on exams before. All right, suppose we take an open box. It can be made out of whatever material you want. It could be cardboard that you can cut real easily. Heck, if it could even be some sort of sheet metal that you can cut with a special type of cutting tools. But anyway, that doesn't matter. So we want to make a box that when we cut off those corners and we fold up the flaps, that would be a flap, 4 flaps. So just, you got to envision that being all folded up. It makes a box, and we want to get the one that has the maximum volume. You want to make a box then that maximum volume means that you can get the most stuff in there. So we're saying here that each side is 24 inches. They don't have to be. Doesn't have to be a square. You could actually do this from a rectangle and still, but the key is we're cutting equal amount off each side, whether it's a square or a rectangle. Okay, so let's take a look at this. So we know it's 24 inches total. And the rest of this we have to kind of come up with ourselves. They're not really giving us the equations, but it's not too difficult. So I'm going to let x be, the best way to do this is let x be the amount you're cutting off here. So x is the amount we're cutting off each side. So then the amount that will be left after you cut the corners off, the length of the box, if it's 24 total, you subtract x from one side, you subtract x from the other. That would make it 24 minus 2x. All right. Let's see. So you have 24 minus 2x on each side. And then volume of that box will be length times width times height. So you have the length and the width of the same value. You have to think about this. Well, if you take that edge and you fold it up, that means x would be the height of that. So just you have to visualize the flat folding up, and that makes x be the height. So there it is. You have length and width, in this case, are the same. I said could technically be different if it wasn't a square, but it would be something minus 2x. You know, say if it was 24 by 16, you know, one of them would be 24 minus 2x, the other would be 16 minus 2x, and then we have x as the height. So you got a little messy algebra there, but it's not too bad. Just one thing I could have done is factored out a 2 here and a 2 here and put a 4 to the outside, but that's okay. And then multiply. This is okay. So I've FOILed that out, and see it's still times x. So we have this function here. So it's going to be 576x minus 96x squared plus 4x cubed. That's your volume. So in other words, you take any number x and you put it in here, it's going to tell you the volume of the box. But we want the one that produces the maximum, but we're not doing it. We don't do it by trial and error. We do it by solving for it. Now let me just go back and look at this domain question here, just to kind of show you why am I saying the domain's between 0 and 12. Meaning if you got some value that was not between 0 and 12, you toss it out. So not only negatives go, but certain positives. Well, obviously greater than 0 makes sense because you're not cutting anything off. But what's that upper limit mean? I'm saying it's less than 12. Because think about it, let's say if you cut exactly 12. Well, if you cut exactly 12 in from each side here, 12 to the middle, 12 to the middle, you've cut the whole thing. That means you've ruined the project, so to speak. So that would be invalid. So it has to be less than 12. So technically, you could cut off 11.99 from each side. It would be a real super thin, weird-looking box, but mathematically it would be okay. But you can't even hit 12 here because 12 is too much. That's going to be very important. You'll see why in a minute. These problems always work this way. So let's take the derivative, 576 minus 192x plus 12x squared. So we set this equal to 0 to get our critical number. And that looks like a big old ugly quadratic, which you can, first thing you can do is these always have a common factor, which is 12. So that makes it so much simpler. So if you factor out a 12 and then divide by 12, and they're always, I say always, I guess the way these problems are generally set up, they're designed to be factorable. I shouldn't say always, but the problems that I put on a test are always factorable. So then that simplifies this, because this would have been a mess to try to factor. Of course, you could have done quadratic formula, which also would have been a mess, or you could have graphed it and found the x-intercepts. But pull out that 12, and then you're left with this, and that's beautiful. X minus 4, x minus 12. Well, we automatically toss out the 12 because of my explanation back up here. It can't touch 12. So there you go. 12 is gone, so we don't have to even test both of these. That means 4 has to be the answer. And once again, I verified it there, but there's no question. That's your only valid critical number. Therefore, it has to be the max. So that means then if that's 4, you can figure out, so 24 minus 2x, you put 4 in there. So let's say you were trying to find the volume. Well, you could put 4 in this equation and get the volume. That would work. Or you can come up with the dimensions 16 by 16 by 4, because that's what it would be if you cut 4 off each side. So you have 16 by 16 by 4. Multiply those together, we get 1024 cubic inches, which is exactly what you would have gotten had you plugged it in this equation right here. And okay, there we go. Let's take a look at this one. Got a line that's 6 minus x all over 2, and we're staying in the first quadrant, and we're trying to find a point on that line where if you then stopped at that point and drew a horizontal line and a vertical line and calculated the area of the rectangle formed by that. But I guess the answer could theoretically be a square, but remember, a square is technically also a rectangle. It's a special type of rectangle. All squares are rectangles, but not all rectangles are squares. So if the answer was a square, that would be okay. Which I think it would be if these were the same same intercepts. Like if that was 6 and 6, it would form a square. Okay, the area of that rectangle we construct will be x times y, and we know what y is here, so let's wrote this as a of x. It would be x times 6 minus x squared, which gives you 3x minus x squared over 2. So now we need the derivative of that, which gives you 3 minus x. And set that equal to 0. We get 3. That means the y coordinate would be 3 halves. So 3 comma 3 halves will give you the maximum area of that rectangle. I'm not a huge fan of this particular problem, but this is a good one to get the concept started for the next one. The reason why is because, yes, you probably would see this. I don't want one where the answer kind of ends up being obvious, which in this case it is. Yes, the x value would always be half of the x-intercept, and the y would be half of the y-intercept whenever it's a straight line. So, but I just wanted to see how the setup of it works. And now we'll do one. If I was going to put this kind of problem on a test, it'd be more like the next one. But that other one would have been too easy. So now we have a parabola, first quadrant. Everything positive, 9 minus x squared. We want to maximize the area. So once again, I just put an arbitrary guess on, or maybe I did put that point there after the fact, but obviously it's not important. But obviously you just know that x will be your horizontal distance and y will be your vertical. So we have x times y, so x, and then times 9 minus x squared. We get 9x minus x cubed. And then we take the derivative, which will be 9 minus 3x squared. Set that equal to 0. So we have 9 minus 3x squared. And we have 3x squared equals 9, so x squared equals 3. So once again, then we only need the positive square root in this case. And positive root 3. See, I like this one, see, so it's not automatically, the x-intercept's 3, so it wasn't automatically half of that. And then you plug the square root of 3 in for the x, and you'll get 9 minus square root of 3 squared is 6. So the coordinate would be square root of 3 comma 6, but therefore the maximum area, though, would be those two numbers multiplied together, which would just be 6 square root of 3. Now these next two problems, I'm going to go ahead and leave the explanation of these out of the video, and I can go back and redo this video later because I'm not going to put these on an exam. So therefore, if I ever decide I want to put this on an exam, then I would go back and explain these in more detail. But I'd like to leave them there in case you're kind of curious. You want to sort of stretch your mind, your imagination there, and try these problems. But this one's trying to say we're adding these two together, and we're trying to find the minimum total area of the triangle and the square together. So we're trying to minimize the sum of that area. And algebra gets really messy on this one. And here's one with a circle and a square. This one gets kind of messy because all the pi's in the answer there. So I'm going to leave those explanations out, but I'm going to leave these in the notes if you're just curious and want to look at them. And that concludes this video.